we have this plan for finding a least squares solution to a system of equations. First, we're going to find the vector in the image of the matrix that's as close as possible to the right-hand side vector b, and then we're going to solve this associated equation. So let's tackle this first step. Let's see if we can find the vector in the image of A that's as close as possible to B. So suppose we have some subspace in Rn and a vector in B. Let's find a vector y in the subspace that's as close as possible to B. Now, in this least squares situation, remember that V is really going to be the image of our matrix, right? That's the particular subspace that we will have in mind when we use this to solve a least squares situation. All right, so V is some subspace, so I'll draw it as if it's a plane sitting in R2. B is some vector, like this, and we want to find the vector down here in V that is as close as possible to B. Now, just geometrically, from our three-dimensional intuition, it seems intuitive that the closest vector is y down here is going to be the vector so that the difference between them is perpendicular to B. So I guess another way to put this is that, so this is b minus y, and this should be perpendicular to all of v, right? That's plausible, but I mean, that's going to take some proof. I guess what we should call y in this case is the projection onto the subspace v of the vector b, right? So this is orthogonal projection here. But we're projecting, instead of projecting onto a single vector, we're projecting onto an entire subspace. And it's actually pretty straightforward to define what exactly we mean by this vector. Geometrically, it's kind of intuitive, but we could write a formula for y if we wanted to. What we can do is find an orthonormal basis, say v1 through vk, for v, and then extend this to an orthonormal basis v1 through vn for Rn. Then we can define the projection of B onto V as just the sum of the projections of B onto each of these basis vectors just for V. So up to k, right? So the idea here is that B itself is equal to the sum from 1 to n of b dot vi times vi. Now this is this equation is true because v1 through vn, that's an orthonormal basis, right? So this equation is true specifically because we have an orthonormal basis. So to keep only the part, right, the part that we want to keep here is the part parallel to v. Well, the parts parallel to v are just the components here where these vi are actually in v, but that's 1 through k. So what we should do is just keep the sum from 1 up to k of b dot vi times vi. But that's exactly this projection, right? This right here, b dot vi times vi, this is the projection onto vi of b because v is unit length, right? Normally in a projection you'd have a divided by vi dot vi, but since we chose an orthonormal basis vi dot vi is 1. All right, and then I guess the thing left to prove is that so we have this projection onto v, we've just defined it. Now we have to show that this difference, B minus this projection onto the subspace B, is orthogonal to V itself. So is orthogonal to V1 all the way up through VK. But that's going to be clear, because if we write down this difference, right? B is this sum up to n. This projection is the sum up to k. So the difference is the sum from I equals k plus 1 to n of B dot Vi times Vi. Is this perpendicular to V1 through Vk? Well, yes, it has to be, because this is a linear combination of sort of the later part of our orthonormal basis. This is the first part of our orthonormal basis, but it's an orthonormal basis, so these have to be perpendicular to each other. So, so we've succeeded in finding this projection, right? We can construct this projection. In actual examples, we would never actually calculate all of these things, right? All of this is just to prove to ourselves that that this projection exists, that it makes sense, right? So we've defined this projection. Now we need to convince ourselves that this projection is actually the closest thing in V to the vector B. And so remember that the characteristic property of y, of our projection, is that B minus y is perpendicular to this subspace. So the next thing we need to show is that given this subspace and the projection of B onto V, so this orthogonal projection is proj onto V of B, we need to show that this vector, which I called y a second ago, is the closest thing in V to the vector B. Okay, so again, we have this subspace, we have a vector B, we have our projection y. Suppose we have some other vector z. So let's take z in our subspace capital V. Okay. What we want to show is that z is further from B than y, right? Because that would mean y is the closest thing in our subspace to the vector B. But another way to say that is that the length of z minus B is greater than the length of y minus B. And the reason this is the same thing is because the length of z minus B, that's the distance, it's this distance, right? Z minus B is this vector, and y minus B is this blue vector. Right? So if we can show that the blue one is shorter than the red one, then that means that y is closer to B than z is. Okay, well, if you look at this situation here, the end of B, the end of y, and the end of z, those are 3 points. Any 3 points in any Euclidean space will define a plane. So we can imagine the plane through these 3 points and just do planar geometry in that plane. Well, in this plane, these two sides are perpendicular, right? And that's because this right-hand side, this yellow side here, is in V, and the vertical side, the blue side, is perpendicular to V. And that means the yellow side has to be perpendicular to the blue side. So we have this right triangle sitting in this plane, so we can use the Pythagorean theorem on this right triangle. The right triangle says that the length of the square of the hypotenuse, well, the hypotenuse is z minus b, so the square of the hypotenuse is the square of the magnitude of z minus b is equal to the sum of the squares of the other two sides. Well, the blue side is the magnitude of y minus b, so that's squared, plus the yellow side, so the square of the yellow side, and that the yellow side is y minus z, so the magnitude of that squared. Well, you know, y and z are not the same thing, so if we throw away this last piece, it makes this whole sum smaller. So this is this z minus b squared is greater than the magnitude of y minus b squared. Okay, so now we know that z minus b squared is strictly greater than y minus b squared, but then we can take square roots, right? Both of these are positive, so if you take the square root of an inequality that's positive on both sides, the inequality stays in this direction, so we get that the magnitude of z minus b is greater than the magnitude of y minus b. And that's what we wanted to show, right? This proves that y is the closest thing in our subspace to the vector b, right? So if we can only find y, then we'll be able to minimize this distance from b down to the subspace V.